Hi everyone, thanks for your interest in my research and welcome to my video. I'd like to present you how we can predict life cycle assessment using machine learning techniques. But why do we need a predictive life cycle assessment? Let's start with an example. Let's imagine you're a chemist and you had the idea that we can use carbon dioxide as a renewable feedstock. This will probably lead to a renewable or environmentally beneficial process for the production of methanol. But how can we know whether this process is environmentally beneficial? We have to compare it to the currently used fossil-based benchmark process. And for this comparison, we can use life cycle assessment as a metric. Life cycle assessment is a holistic method taking all life cycle stages into account. This is on the one hand promising because we avoid emission shifting between these life cycle stages, but on the other hand, we require a large amount of data because we have to describe each of these life cycle stages. And unfortunately, if we only had the idea of a process, then we usually don't have this data. So let's take a look on the time scale when we will achieve this data for our assessment. Starting with the idea, we will first make some simulations, maybe we need some experiments in the lab, and finally we have to make a detailed process design. And with increasing development, we also increase the availability for our data, but we also decrease the mitigation potential because we already made some specific design decisions during process design, and if we want to change this design in the end again, then this will come with high costs. So it would be preferable to have a life cycle assessment just in the beginning. However, we don't have the data for an assessment there. So what we need is a predictive life cycle assessment which requires as less data as possible. In the literature, there were already proposed some predictive life cycle assessment approaches which are all based on the molecular structure of the main product. If we take our example, methanol again, then we can translate the structure into a numerical representation by counting the number of specific atoms or the number of specific functional groups. And we can then pass this vector to an artificial neural network. And as proposed in literature, we can obtain kind of these results. This is a copy from the paper of Song et al., and they predicted the global warming impact in terms of kilograms CO2 equivalent. And this prediction looks quite promising. As you can see, they achieve an R² on their testing data of 0.48. So let's apply this method on our example from the beginning. We will obtain these results. What can we see? You can see the global warming impact on the y-axis, once estimated for a fossil-based route and once for the carbon dioxide route. And you can see that first, we overestimate the impact itself. And second, you can see that the process or the AMN is not able to distinguish between our process alternatives. This is quite obvious because we only used information about the molecular structure as an input. So this neural network is intrinsically not able to distinguish. So I want to tackle two problems in this presentation. The first one is we have to substitute these component-specific features by, let's say, more process-specific features. And the second problem is that artificial neural networks are not well suited if we only have limited training data, which is the case in application of lifecycle assessment. So let's start with the features. We propose a fully automated framework where we can use the SMILES code as one of two inputs. And based on the SMILES code, we can calculate molecular fragments or number of specific atoms. But we can also use quantum chemistry and quantum mechanics to calculate, for example, the enthalpy or the entropy of our main product. But these are the component-specific features I already described for the literature network. So we have to extend these features by using so-called process-specific features. And we can calculate them just based on the reaction equation for our process we want to predict. Using quantum chemistry and pinch-based process models, we can calculate, for example, the phase equilibria or chemical equilibria. And most important, we can translate the reaction equation itself into a lower bound of our impact. We do so by summing up the impact of the reactants, and the resulting impact has to be a lower bound of our prediction. As I already, in total, we will obtain approximately 5,000 possible features if we combine these two kind of features. As I already mentioned, we propose a fully automated framework. We start with the reaction equation and the SMILES code as an input. We can generate approximately 5,000 features from this. And afterwards, we have to select the most promising features because we can't use all 5,000. We use a stepwise regression for that, and we can then select the 10 or 20 most promising features out of this. The next step, we have to set up a suitable regression model. But the question is, what is a suitable regression model? So let's have a closer look and compare these models based on 4 criteria. The first one is the bias variance trade-off. The bias variance trade-off describes whether we have a too simple model or a too complex model, because a too simple model comes with a high bias error, which means that this model is too simple and we thus underfit the underlying function. On the other hand, if we have a high complex model with limited training data, then we tend to overfit. So we have a high variance in our prediction, resulting in high prediction error as well. So the perfect model will well balance the bias and the variance error, resulting in a minimum prediction error. The second 2 criteria are the generalization ability and extrapolation potential. We can explain these 2 criteria in combination because they both refer to the range from which we try to predict. While the generalization ability describes whether the prediction is lying inside our applicability domain and whether it's good or not, the extrapolation potential describes how good we can predict values which are not inside our applicability domain. The last criterion is quite obvious because we want to use the prediction of life cycle assessment as a decision or to support a decision during process design. And for this, we have to rely on our prediction and we have to quantify how reliable or how uncertain our prediction is. If we now try to classify the artificial neural network in terms of these 4 criteria, we can see that, especially if we have only limited training data, that we have an okay bias variance trade-off and we have an okay extrapolation potential, but we lack in terms of generalization, and the artificial neural network has no uncertainty assessment intrinsically included. So what to compare with? What's a better machine learning model for prediction? One opportunity is the Gaussian process regression. The idea of Gaussian process regression is that you generate a sample of functions, and during the training, you fit probability distribution, which function fits the prediction most. And due to this distributed function approach, we intrinsically include an uncertainty assessment in our regression model. Now, this sounds quite promising for the application of lifecycle assessment. Let's take a look again on the criteria how the Gaussian process regression will perform there. You can see, just based on the literature, that they are described to have good bias variance trade-off with limited training data. They are suitable for high generalization ability and a high extrapolation potential. And due to the distribution approach, they include an uncertainty assessment. So let's compare the artificial neural network and the Gaussian process quantitatively. To do so, we have to train our models. And for training purpose, we use 308 chemical processes we calculated based on the AICHE market database. We include 168 chemicals. And from these 300 processes, we excluded 10% for testing. We have chosen them manually just to be sure that we have multiple processes leading to the same main product, just to compare whether we are able to predict or to distinguish between several processes leading to the main product. So let's come to the prediction. On the left side, you can see an artificial neural network which is trained on our data, but which is set up as the proposed network by Song et al. And on the right side, you can see the Gaussian process regression. In the first step, we trained the Gaussian process regression only on the molecular descriptors as described in light green. You can see the prediction on our training set, and in dark blue, you can see the prediction on our test set. The third thing is that we have a wide scattering in the prediction of the artificial neural network, especially on the training set. And in contrast, the Gaussian process regression predicts quite a more stringent line. However, it's a bit twisted against the 45-degree line, which indicates a perfect prediction. But to quantify the prediction performance, we can only focus on the test set because this is the real prediction. So let's exclude the training set and calculate the R squared as a measure for our prediction performance. On the left, you see that we obtain an R squared of 0.22 for our test set using the component-specific artificial neural network. And on the right, we could increase the prediction performance, leading to an R squared of 0.42. This is mainly obtained because we have an increased prediction performance on lower targets, ranging from 0 to 10 kilograms CO2 equivalents. And the question is now, why don't we hit the higher targets? This is the case because to each of these high points, we have a regarding point describing the same main product, which we hit quite well. So for this example, we have 2 points or 2 processes producing methyl methacrylate. And the first one we can predict quite well, but the second one we cannot distinguish because we only have molecular descriptors. The same is for butadiene or our example from the beginning, methanol down here. So let's apply our new derived process-specific features in the next step. You can now see the process-specific Gaussian process regression on the left and the already known molecular-specific Gaussian process regression on the right. If we now draw a line through our prediction of methanol, you can see that we obtain the same prediction on the right. And this line is shifted on the right because on the left because we're now able to distinguish. Let's have a closer look on this example. You can see here in gray the literature value. We have in dark blue a prediction using a component-specific ANN. This is the ANN which is proposed in literature. In light gray and light blue, we have the prediction of our process-specific ANN, which means that we use the artificial neural network from literature, but we use our new features. And in green, you can see the process-specific Gaussian process. What you can see is that, first of all, the component-specific ANN, of course, is not able to distinguish between the alternatives. However, the process-specific ANN using our new features is already able to distinguish. Additionally, you can see that the Gaussian process regression has a lower prediction error because we do not overestimate our real targets so much. However, we still overestimate. But what you can see is that both approaches using the process descriptors are able to distinguish and they can predict this trend correctly. So for a first guess in process design, this would be quite promising. But if we have now a closer look on the reliability of our prediction, you can see that we have a large uncertainty interval. This is true for both, for the ANN and the Gaussian process regression. So, to be honest, we are not able to distinguish between these alternatives anymore because these uncertainty intervals quite overlap. So, we have to improve our prediction in terms of uncertainty. This is further work we have to do. With this, I'd like to conclude my talk. I've shown you 4 criteria based on which we can classify suitable regression models for LCA application. I've shown you that Gaussian process regression can outperform artificial neural networks, especially on low target values. And we introduced new type of features to be able to distinguish between process alternatives. In the end, I've shown you an example where you can see that we can distinguish between process alternatives, but we have to improve the intervals still overlap, and we are thus not able to make a reliable prediction. Thanks for your attention. If there are any open questions, feel free to write in the chat or meet me in my live session on Wednesday at 5 p.m. Central European Time. Thanks for watching.